In my first lecture, I gave you an overview about structural geology. And one of the things that we have learned, that there are three very important aspects. One is the strain, the deformation of rocks. One is the stress, the forces. And the third, is what the material is. Maybe you remember the examples with the cookies that I was deforming in front of you. And now I will go through all these three topics one by one. First, I will do strain, because that is the easiest. Strain, deformation, is an essential part of what happens when rocks are subjected to forces in the earth. And I will explain to you how we recognize strain in rocks. I will explain to you how we model this mathematically. And then I will show you some of the techniques which are possible to measure strain in rocks. This will be today's lecture. Now, just like I told you that you can learn a lot about deforming rocks by squeezing cookies, you can learn a lot about deformation from studying other things than rocks. Deformation is not something that is only in geology. It is everywhere around you. It is in many aspects of engineering, for example, but also in your daily life. When you stir your muesli with yogurt every morning, you are doing a lot of deformation in your breakfast. And here is a very nice example. This is an actual painting by William Scrots, painted in 1546. And he painted the King Edward VI. Why do you think that this painting looks like this? The reason is that he had to paint it to fit in a very long corridor. And when the king came into the corridor, he had to see himself. What the king had to see is this. Of course, you know that if you look at this painting from the side, you are going to see it like this. Therefore, if you see my hand from the front, and if I turn it, you see a deformed or a distorted version of my hand. And this was what William Scrots invented, to paint his king in this way, so that when he came into the long corridor, he saw himself and saw his big nose. This is a very simple example of a homogeneous deformation, and I will in this lecture tell you about the mathematical basis of how to describe homogeneous deformation. Of course, homogeneous, we talked about it in the last lecture, has to be defined as a function of scale. How big is it? And there we have a very important concept, and it's called the representative elementary volume. REV, representative elementary volume. This is a very simple little picture with lines and circles that I made for you. And now I'm going to deform this homogeneously. Okay. What you see is that every circle becomes the same ellipse. The big circle becomes an ellipse which has exactly the same aspect ratio as the small circles. And you can clearly see that this deformation is homogeneous, because this is true for every ellipse. If these two ellipses would now look differently, then you would have to say the deformation is only homogeneous on the right side of the picture. Okay, so homogeneous deformation in a very basic level means that straight lines remain straight, circles become ellipses, and as we will see later, ellipses become ellipses. Okay, so here is the next question, a little bit of a trick invented by my colleague Wim Means. Here is the original object, and it has been deformed. Straight lines remain straight. Is the deformation homogeneous? No, because there is one more very important consideration. Parallel lines must also remain parallel. You could see that this is not homogeneously deformed by drawing this line here between the diagonals, because that line is actually becoming curved. So not all straight lines remain straight in this diagram. I tried to fool you, but I didn't. Okay, here's the next question. Is this homogeneous deformation? This is the original, 12 years ago. There's more hair. Is this a homogeneous deformation? You all are nodding yes. What I did here is I sheared the picture using Photoshop, and the deformation is homogeneous. Is this a homogeneous deformation? I don't think so, because, for example, the straight line that I would be able to draw from the top of my hair down to here has now become curved. What is very important is, if you want to understand deformation, is that you have to have some kind of a notion of how the undeformed object looked like. So here is one. Is this a homogeneous deformation? Most of you are nodding. It could well be homogeneous deformation. Why? Because we all know Mickey Mouse, and we have seen it many, many times. And we can imagine, yes, this is just a little bit flattened version. So it is understanding deformation in rocks, where we are seeing the products, the deformed products, always involves knowing how it looked like before. That's very important. And coming back to this representative elementary volume, well, here's a very nice little example. I take my beam of rock. This could be a very thick, 100-meter thick layer that I'm squeezing in the alpine orogeny. This is how it looks like afterwards. And here I can define this small area which deforms homogeneously. And if I want to describe the deformation of a very complex defolded rock, I would have to divide it into small elements which have been deformed homogeneously, so that each element I can give a simple mathematical description of the deformation. Representative elementary volume. A simple example is a fold. There is a very simple demonstration. I can take this sponge and bend it. And if I would now paint little circles on the sponge, I would see that on the outside the circles will stretch, and on the inside the circles will shorten. And in the middle there is this neutral line. This is quite well known in mechanics. So the deformation here is not homogeneous. It's heterogeneous. But inside each of these elements it is homogeneous. It changes from element to element. So why do we need strain? Why do we need to be able to describe strain, to understand strain? Because if we want to understand a mountain belt, like the Alps or the Himalaya, then we have to be able to measure how the strain formed and what the strain is in each part of this mountain belt. To illustrate this, and you will get much more information about these kind of techniques later in your study, I will show you a profile of one of the big folds in the Alps. It is called the Morkel Nappe. So what you see here is a profile. It is about 20 kilometers long. It is in the middle of Switzerland. It is about 5 or 6 kilometers high. It is a section through the earth. And these lines are actually rock layers which have been folded and trusted over each other. Very complicated. And one of my colleagues went into this mountain belt and measured the actual ellipses, which all used to be circles in the beginning, so that he could make a map in this section of how the rock was deforming. And look here at the bottom, where these rocks were thrust over a very strong granite. There is a lot of flattening, there is a lot of deformation, but for example here there is very little. So in mountain belts, strain is heterogeneous, of course, and we need tools to understand this strain. Okay, so these were some nice examples. Now we have to again go to the mathematics and try to understand how to describe strain mathematically. So let's look at this little simple coordinate system. The first axis is x1 and the second axis is x2. And I have a point here, small x, and I deform it, I transform it, and it becomes x big with a slash. And what I want now is I want the equations which transform this point to its new position. And the equations that I choose to do that are these. x1 is the x or the one coordinate of this first point, and x2 is the second. And now I choose four numbers, d11, d12, d21 and d22, these four, to make this transformation. So the new coordinate of the point is the result of this equation, and the new vertical coordinate is this one. You can write these four numbers in this very simple matrix, the D matrix, this one, this one, this one, and this one. And this transformation, you have learned all about this maybe in secondary school or certainly in your linear algebra lectures, is a very powerful equation in 2 dimensions because it transforms objects homogeneously. So I have now shown you how to transform this point to there, but I can of course transfer 1,000,000 points and then give you the new object. For example, if I take a circle and I transform all the points on the circle, then I become, or I get, an ellipse. To illustrate this, we have a little computer program that I'm going to demonstrate to you. You can download it from our website, and then you can exercise, try out different parameters. It's very easy, and it's very easy to learn. I would advise you very strongly to do that, because in the exam you are going to get questions related to this. Okay, so don't tell me that I haven't warned you. So how does this work? I have my initial point. I hope that you can read this. This is the coordinate of this point is 4, 1. 4 this way and 1 up. This is the point. And these are the 4 numbers, 1, 1, 1, 2, 2, 1, 2, 2. And these two are 1 now, and this is 0, this is also 0. If I change that, going to say 0.1, then you can see that the new point is red and the old point is blue, and I've moved it a little bit. I can maybe make this 1.1 or 1.2, and it is moving there, and so forth and so forth. I can choose an infinite number of values for these 4, and I will always get a new position. One very special combination, which is 1, 0, 0, 1, that is the combination which leaves everything in the same place. Okay? So this is the transformation which we have programmed here, and you can play around with it. You can check out where points come after this transformation. Now here it is a little bit more complicated, because what I've done is I have put in many points which define a circle. It's all these points here. The transformation is the same. Whoops! Who is moving my beamer? Can you put it back, please? Okay. And now here I've put 1, and you can see that the circle has become an ellipse. If I put the